All right, here we are back to the grind, ready to work our way through chapter 9. The way the class is constructed as of the time of this narration, you've just finished your second exam, so hopefully it went well. I suppose it's possible it went not quite as well as we would have wanted. To be honest, I think if you've been doing these narrated solution slides, if you've been really doing the problems, like actually doing them and not just listening to me doing them, but doing them and checking your work, I am pretty confident you did well. But regardless, doesn't really matter. The past is the past. It's time for us to just focus on the present. It's time for us to focus on the future. It's time for us to move forward. Unattached from any type of kind of worry about, oh, I'm going to pass, I'm not going to pass, whatever. We're going to do this for the love of the game. We're going to do this for the sake of knowledge. And what is it we're doing for the sake of knowledge? It is chapters 9.1 and chapters 9.2 that we are doing for the sake of knowledge. Hypothesis testing for a population mean when the population standard deviation is known. So I guess I should just again reiterate, and I'm sure I've already done this in the actual narrated slides talking about the course material, but chapter 9 really parallels chapter 8, right? In chapter 8, we learned 3 different types of confidence intervals. A confidence interval for the mean when the population standard deviation is known. A confidence interval for the mean when the population standard deviation is unknown. And a confidence interval for a proportion. Not surprisingly, we are now going to learn 3 types of hypothesis tests. A hypothesis test for the mean when the standard deviation is known. That's 9.1 and 9.2, so that's what we're going to focus on right now. A hypothesis test for the mean when the standard deviation is unknown. It's 9.3, I believe. And a hypothesis test for proportion. So we're just sort of redoing everything that we did in chapter 8. So again, all that hard work we put in is going to help us be able to kind of get through this work all the more easily. So 9.1, 9.1 is pretty straightforward. It's just a lot of like fill in the blanks type problems and short answers and things like that. They're fairly straightforward definitions, so I'm probably not going to talk over them too much. I don't think there's a whole lot that requires elaboration. So again, null hypothesis states that the parameter is equal to a certain value, right? We always say that the null hypothesis is a statement of equality, while the alternative hypothesis states that the parameter differs from this value. 17 through 20 is just kind of definitions about type 1, type 2 errors. I usually do ask a question on the exam along these lines. My question, actually, I have to admit, is probably a little bit even more difficult than theirs, because they kind of really just tell you we reject, we fail to reject. I'm usually going to kind of write it out in words, and you'll have to actually kind of like read my words and then infer that we rejected or failed to reject. But you definitely want to make sure that you're comfortable with these problems. Again, it's just definitions, right? A type 1 error is just rejecting the null hypothesis when we shouldn't have. A type 2 error is failing to reject the null hypothesis when we should have. So make sure you know these definitions and make sure you can apply them to these problems. This is just a definition of the p-value. I guess it's good to know. I'm probably going to do a lot more problems where you actually have to calculate the p-value or use the p-value. I don't know that I would on a test just straight up ask you the definition of a p-value. 29 is a pretty important one. In fact, it's something that you should put a couple stars next to with your virtual stylus or whatever. Right, the smaller the p-value, the stronger the evidence against, right, H not just means the null hypothesis. That's extremely true. It's a pivotal fact. Ideally, I want that to make sense. But even if it doesn't make sense, I want you to memorize that. You need to sort of know that fact. The smaller the p-value, the stronger the evidence against the null hypothesis, right? The follow-up question is, okay, well, how small? How small does it have to be for there to be enough evidence for me to finally say, okay, enough is enough. I'm going to reject this null hypothesis. I no longer believe it. Well, that's where that significance level, that alpha, comes into play, as we'll see with some actual problems coming up. So here's problem number 35. We've actually switched to 9.2, by the way, so this is actually page 441. So here we're actually doing some hypothesis test problems. I think I do like something like 35 to 41. They're all kind of generic problems. There's no context, so you're just kind of really kind of practicing the basics here, the fundamentals. So they set up the null and alternative hypothesis for you. They tell you the size of the sample. They tell you what that sample mean is. And then, right, they very clearly say the population standard deviation is, right? I bolded that because that is a keyword. Again, when we're doing the homework problems, it's easy to know which of the 3 hypothesis tests we're doing. On an exam, it's not always so easy, right? So we have to have an appreciation of what it is that's guiding us to do a particular test. In this example, we're doing a test of the mean. They've made that very explicit, and we know the population standard deviation. And because of that, we're going to do a z-test. So how do we do a z-test in our calculator? Right, I've kind of walked you through this in the other narrated PowerPoints, but you hit stat because it's stats class. You go over to test because this is useful on a test. And then I actually don't believe you're going to have to move your cursor anywhere. I think it just starts by default on z-test. But regardless, one way or the other, you're going to select z-test. Then move it over to stats if it's not already, and then kind of like your confidence intervals, you're just filling in numbers, right? So the book gave us those numbers. The conjectured mean, the mu naught, is 50. The population standard deviation, again, how cool is that? Our calculator knows if we picked z-test, we know what that population standard deviation is. It gives us that sigma symbol. Remember, that sigma symbol just means population standard deviation, so it knows to ask for that. It's a nice check that we're using the right test. We put 56 for the sample mean, 75 for our sample size. It told us very specifically that our alternative is that mu is greater than mu naught, right? Greater than the 50 that we specified above. Then we highlight the calculate and hit enter. And there's the output. Usually there's just sort of 2 numbers that we care about. So that z equals 2.59, or I guess maybe that round is 2.60. That's called our test statistic. So that's basically saying that our sample mean is 2.6 standard deviations above the hypothesized mean. And that p is our p-value. That p-value is really the most sort of fundamental, metric, the most important number, right? People write poems, they write sonnets, they write haikus. Ooh, that'd be a good extra credit problem. Write a haiku about the p-value, right? Because it's so important, it's so powerful, it's so moving. It stirs the soul, even as it powers our statistics. So here our p-value is 0.05. So those are usually the 2 sort of pieces of output that we're getting from the calculator. Remember, all types of hypothesis tests have the same 4 steps. Set up the hypotheses. The book did that one for us. Calculate your test statistic. Well, the calculator does that. Find your p-value. Calculator did that. And then make your conclusion. So the hypotheses we often have to set up ourselves from the context of a word problem. Steps 2 and 3, the calculator does for us. And then step 4, we have to do ourselves with the information provided by our calculator. So, right, book says, what's the test statistic? There it is, 2.598. Then the book asks us to sort of make some conclusions. So the conclusions require 2 things. They require a p-value. They also require something referred to as an alpha, or sometimes it's referred to as a significance level. And that can vary from problem to problem in like textbook world. In real world, we almost always just use 0.05, but the book likes to mix it up and come up with all kinds of different alphas, I guess, just to make our life feel a little bit more interesting. So it says, all right, well, would you reject the null hypothesis using 0.05? And again, we always just compare. We compare the p-value to our alpha. Remember, we said just a few slides back, we said the smaller the alpha, the stronger the evidence against the null hypothesis. So that means if the p-value is small, say smaller than our alpha, that's strong evidence against the null hypothesis, right? So bye, Felicia, right? We're going to see you later. We don't believe in the null hypothesis. So in this case, our p-value 0.005 is less than 0.05, so we reject the null hypothesis. Part C, 0.005 is also less than 0.01, so right in this situation, using this more stringent alpha, we would also reject the null hypothesis. And I've already showed you the calculator, so I think I'm going to show it on some problems coming up, but I think like 36 through 41, I'm just going to have the answers here. So you should be able to check your work. Again, you're just getting test statistics and p-values. Then you're comparing those p-values to the alphas that they provide you. Test statistics and p-values, and then comparing the p-values to the alphas that they provide us. More test statistics, more p-values, and then comparing the p-values to the alphas that they provide us. So they're always giving us the same alphas, I think, in this little batch of problems. Looks like it's always 0.05, 0.01. Here they kind of, looks like they mix it up a little bit. This is just like a definition of a p-value, so just a definition problem. 40 is just 39 all over again. The book tends to do that. They tend to do two problems back to back as like the same type of problem. I think presumably because one will be odd and one will be even. So right, I think kind of their thought is you do like the odd problem and then you check your answer and then you reinforce it by doing the even problem. So 39 and 40 are pretty much the same problem. And then just kind of a run through of like how you use p-value. So if our p-value is 0.02, what would you do if alpha was 0.05? Well, 0.02, that's like 2%. 2% is less than 5%, so we reject. Reject is just saying that it's statistically significant. So statistically significant is just another way of saying that our p-value is less than our alpha. 2% is not less than 1%, so in that case, it's not significant. 2% is less than 0.05. So actually here it's just changing the language. So oh whoops, looks like a little bit of typo. I go A B A. Sorry about that. Should be A, of course, A B C D. So A and C are really the same problem. They're just kind of changing the language, but the language means the same thing. Statistically significant means that you're going to reject the null hypothesis, and then B and D are really the same problem. Just want you to acknowledge or notice that the language is equivalent. All right, and then here we are. So 51, and I think maybe a 53 after this. These are probably, I mean, again, all the stuff we did leading up to this was important practice, but in terms of what you'll see on a test, this is probably the type of problem that I would be most inclined to put on a test. So here's a presumably real life study, 2015. Showed that the mean time, the average time spent per day browsing Netflix for something to watch was 19.3 minutes. That's just, holy smokes, that's just trying to like find something to watch. It's not even including how much time we spend actually watching it. That's a pretty serious, those are some pretty serious show hole shenanigans. Then it says, assume the standard deviation is, and it uses that symbol sigma, equals 8. Again, I boldface it because as soon as I see that sigma, that's telling me, boom, z-test. And then it says, okay, suppose a simple random sample of 100 visits taken this year is a sample mean of 21.5. Uh-oh, looks like maybe we're getting even more indecisive. A social scientist is interested in knowing whether or not that mean time browsing Netflix has increased. It makes sense, I guess. Netflix has more and more and more and more shows, so presumably it would take us longer and longer and longer to settle on something for us to watch. So I bold-faced that statement because that's what's going to help guide us in terms of setting up our hypotheses, which I think we do on the next slide. So, right, we want to know whether or not the mean time browsing Netflix has increased. So part A is like our step one, set up the hypotheses. Our null hypothesis is that the mean time hasn't really changed. It used to be 19.3, it's still 19.3. The null hypothesis is always a statement of equality. It's like the status quo, right? No effect or no change. The alternative hypothesis, H1, is that mean time watching Netflix, that mu, has increased. So it used to be 19.3, now it's more than 19.3. So all right, step one, check, that's done. Step two and step three, well, we're going to need our calculator to do those things. So it asks us our test statistic. Actually, I guess it asks us step four for C. It tells us to make a conclusion, but we'll of course need a p-value to make that conclusion. So here's our beloved calculator. Remember, stat, test, z-test. Fill in all the information, all provided in that slide. Again, once we've actually written down those null hypotheses, that last little line is fairly straightforward. In this case, we want to know whether mu is greater than mu naught, right? Greater than that 19.3. Plug all that into our calculator, put the little cursor over calculate and hit enter. And here we are. So there's our test statistic, 2.75. There's our p-value, looks pretty small, 0.003. And so let's use that information on the next slide to make our decision. So our test statistic is 2.75, right? The observed sample mean is 2.75 standard deviations, almost 3 standard deviations. That's a lot. Above the hypothesized mean of whatever it was, I think 19.3 minutes. Our p-value is 0.003. Because that's less than 0.05, we're going to reject the null hypothesis. What does that mean to reject the null hypothesis? It means there's sufficient evidence to conclude that the mean time browsing Netflix has increased, right? That's like the conclusion that we, as high-paid, highly satisfied statisticians, are going to pass on to our client, the hapless social scientist, right? At the end of the day, like, we crunch all these numbers, we know what they mean, but we're going to sort of soften the message for the social scientists. We're going to say, oh yeah, looks like the amount of time people are spending browsing Netflix has in fact increased. That's our answer to the question. All right, number 53, sort of a silly problem. Are older men shorter than younger men? So we have some information from a national health statistics report. Says that the mean height for all men is 69.4 inches. We took a sample of, quote, older men, 300 of them between ages 60 and 69. It does seem like that at some point we do start to shrink a little bit, doesn't it? I have noticed this phenomenon as I spend more and more time in whatever assisted living, old folk communities. I'm not sure what the correct term is, but I've had and have grandparents. I visit them a lot, and it does seem like maybe they're not quite as tall as they used to be. So of the sample, we find that their average height of these older gentlemen is 69 inches. And so public health officials want to determine whether the mean height for older men is less than the mean height for all adult men. So again, right, I kind of highlighted that that is less than the mean height of all adult men. So that helps us set up our null hypotheses, right? All adult men are 69.4 inches. We conjecture that older men for whatever reason, are smaller than that, so that is that their average height is less than 69.4. And then B kind of slides in a little bit of extra information. It says, okay, well now assume the population standard deviation is, they use that little sigma symbol, 2.84. Boom, population standard deviation. That immediately tells me z-test. It says find the test statistic, which we'll do on the next slide. It says make a conclusion, which will require a p-value, which we will also calculate on the next slide. So there's our high-powered statistical computer. We fill in all that information. Right here, our alternative hypothesis is that it's less than 69.4. So notice I picked that middle option, whereas before I picked the rightmost option in terms of setting up my hypotheses. Then I put the cursor on calculate, hit enter. So my test statistic is negative 2.44, right? The observed average height of older men is 2.44 standard deviations below, right? Below because it's negative, below the average height of all men. So that is quite a bit, like 2.5 standard deviations. And so not surprisingly, there corresponds with it a small p-value. How cool is that? 0.007. So our test statistic, negative 2.44. Our p-value is 0.007, which is less than 0.01. Anytime our p-value is less than our alpha, our significance level, we reject the null hypothesis. What does that mean? Are older men smaller, yes or no? We would say yes. There is sufficient evidence to conclude, that should be that the mean height for older men is less than that of all adult men. And I believe that we're done. So again, remember, it's best practice to do these problems yourself, to attempt these problems yourself, and then listen to my narrated PowerPoints. And if you're not sure how to do one or two problems, okay, listen to me do one or two problems, then pause it and do the rest, right? I should have really reinforced after we did 51, I should have harped on you, I should have nagged you to make sure you do 53 by yourself before looking at my solutions, right? Again, we learn by doing, not by listening, okay? Listening helps, but it's the doing that really gets the job done.